A vehicle travels down an empty, winding road at night. Without warning, the brakes lock, and the 2-ton machine shudders to a dead stop. The automatic emergency braking system triggered because the onboard AI detected a pedestrian in the vehicle's path, but the road is completely clear. To find the flaw, a traditional automotive safety engineer working under the ISO 26262 standard would pull the software logs. They would look for a broken explicit rule, a failed if-then condition in the code that caused the false positive. Modern autonomous perception systems do not use explicit code. They rely on deep neural networks, massive statistical engines where decisions emerge from the interactions of millions of numeric weights, heavily dependent on the data they ingested during training. This creates a severe engineering dilemma. If the model outputs the correct label for pedestrian, but we cannot point to the specific logic of why it chose that label, the system cannot meet the safety requirements of a road vehicle. To establish rigorous quality control over these models, the automotive engineering community recently published ISO PAS 8800. This standard provides a concrete framework for inspecting the internal mechanics of artificial intelligence. The standard requires a structural change in strategy. The neural network is no longer treated as a single entity, but as a collection of distinct, testable software units. Validating a self-driving car means moving past simply scoring its final predictions on a test track. We have to open the architecture and mathematically audit the logic happening inside the model. You cannot simply slice a neural network layer by layer to create a software unit. Individual neurons do not perform isolated, human-readable functions. They form a distributed representation, meaning the concept of a pedestrian is scattered across thousands of nodes simultaneously. Instead, engineers divide a standard object detection model into 2 distinct functional halves: the backbone, which extracts high-dimensional features from raw pixels, and the head, which uses those features to make the final decision. This glowing cross-section is the latent space, a tensor grid acting as a logical interface. It forms a clear boundary, separating the backbone unit from the head unit. Here, the data must consistently hold the distinct spatial signature of a human silhouette. When engineers retrain the model with new data, the internal weights will shift, and the exact numerical values within the latent space will change. However, the mathematical intent, the contract to provide pedestrian geometry, must remain stable. Defining this boundary allows teams to decouple the architecture. They can test the backbone's ability to isolate shapes independently from the head's ability to draw bounding boxes around them. Isolating the latent space provides a clear vantage point. It gives engineers the exact mathematical interface required to interrogate what the AI is actually seeing before it commits to a decision. We can apply this unit testing framework directly to the ghost braking incident using visualization tools like Grad-CAM. This split screen projects Backbone's latent feature map over the original camera feed. The red heat map isolates the error. The model is not reacting to a human shape, but perfectly tracing a jagged tree shadow stretching across the asphalt. To correct false correlations like this, engineers deploy Concept Bottleneck Models, or CBMs. A CBM structurally forces the network to predict intermediate, human-understandable concepts within the latent space. Before the head unit calculates a final bounding box, the model must explicitly identify features like legs or a torso. The latent space must also maintain spatio-temporal consistency. The mathematical representations of objects moving through this space must obey the physical laws of the real world frame by frame. If the latent coordinates indicate a pedestrian has moved 10 meters across the highway in a tenth of a second, or if an object vanishes entirely between frames, the system instantly flags a perception error based on physical impossibility. By auditing the latent space for conceptual accuracy and physical plausibility, safety teams catch processing errors at the source, preventing false positives from ever reaching the braking system. When external conditions degrade, like a dense fog rolling rapidly across a dark highway, the vehicle's camera data completely loses fidelity. A secure AI architecture must have the capacity to recognize its own operational limits and quantify when its inputs are no longer reliable. This introduces 2 distinct metrics of doubt. The first is aleatoric uncertainty. This is the inherent noise contained in the sensor data itself, the physical static caused by rain, glare, or fog. The second is epistemic uncertainty. This occurs when the model encounters an out-of-distribution scenario, a visual pattern or environment the network was not exposed to during its training phase. Engineers use Monte Carlo dropout. This scatter plot maps latent space outputs. A wide, blurry cloud indicates high epistemic uncertainty. A real-time line graph tracks this variance, acting as a hard trigger for safety protocols when crossing a defined threshold. The system responds instantly. It de-weights the unreliable camera unit, increases its reliance on active sensors like LiDAR, and safely reduces the vehicle's speed. Quantifying uncertainty enables the system to monitor its own reliability. Rather than guessing, the AI can trigger a calculated, risk-aware handoff the moment it reaches the edge of its training. Resolving single failures and measuring uncertainty handles localized errors, but engineers must also mathematically prove the entire neural architecture has been sufficiently tested. Black box testing on a track measures final outcomes. ISO PAS 8800 demands white box structural coverage, a complete map of the internal activation states during testing. This shows neuron coverage. As massive night driving data processes, pulses travel through the grid, the red clusters are dead neurons that failed to fire, indicating structural deficiency. KMNC testing goes deeper, using a segmented chart to measure a node's exact utilized mathematical activation range. The standard also adapts traditional MCDC code coverage into neural networks through a metric called sign-sign coverage. Sign-sign coverage proves the logical causality between layers. It verifies that a specific feature extracted in the backbone consistently causes the corresponding output in the head unit. Mapping these dark spots and untested ranges stops engineering teams from simply driving random miles to gather data. It gives them precise mathematical targets for data augmentation. Structural coverage metrics provide a mathematical audit of the test suite's efficacy. They replace broad assumptions with a precise map of where the network has and has not been adequately stimulated. Once the individual software units are optimized and verified, they must be synthesized back into a complete system. ISO PAS 8800 directly integrates neural network testing into the traditional systems engineering V model, ensuring AI development follows the same lifecycle as steering or braking hardware. During integration, engineers deploy verification monitors. These monitors constantly evaluate the latent space outputs against established ground truth data to ensure no performance degradation occurs as the units are connected. This workflow operates inside a CI/CD pipeline. Every time the model updates, data blocks must clear automated checkpoints. Only when all coverage and uncertainty metrics generate green lights can the build proceed, compiling into a final certified readout. That readout forms the safety argument. It is the empirical proof required by regulators and the public to demonstrate a vehicle is road-ready. The AI industry is adopting the strict quality control standards of traditional automotive engineering, prioritizing verification over pure performance optimization. A modern autonomous vehicle navigating an intersection relies on massive streams of data. By structuring data and auditing internal mechanics, we create a governable architecture. This rigorous verification is the necessary step toward integrating neural networks into the safety-critical systems of modern vehicles.